So, at this point, if you remember what we've done in this class so far, we haven't necessarily done a whole lot. We introduced the class with two big questions. They were the two questions that were going to guide us for the first half of this course. Those two questions were, how do we find the slope of a tangent line to a curve at a point? And how do we find the instantaneous rate of change, the instantaneous velocity of a curve given a position function? And we showed, on the very first day, we showed our idea for the answers for those two. And we said that those two are really the same question. And then we haven't addressed those questions since. Because we had to bring in this idea of a limit to be more precise in what we mean when we talk about these questions. Okay? So let's just revisit them real quick. Okay? Let me put this back to page width so it's a little bit wider. Let's try 150. Okay, let's do that. That looks a little better. Okay. All right. So remember, we asked the question: how do we find the slope of a tangent line to a curve at a given point? And then suppose we're given the position function of an object. How do we find the instantaneous velocity? It's just the word instantaneous goes there. Okay. So just as a reminder, because we never defined the slope of a tangent line. Okay. But just as a reminder, I gave you the little diagram to give you sort of an insight to it. If this was my curve, then the slope of a tangent line at a point was a line where those arrows were coincident with each other at the point that we were interested in. Okay? Today we'll actually define the slope of a tangent line. Okay. So we actually did this last time. We did this the first day of class. Okay. And remember we said, okay, it's hard to find the slope of a tangent line. How come? Because to find the slope of a tangent line, to find any slope, we've always needed what? 2 points. But given a tangent line, we generally just have 1 point. Even if there are other points, we don't know how to find them. Okay? So what was our strategy? Our strategy was to take some arbitrary ordered pair on the function, call it x comma f of x. And then for this point right here, we found the slope of the green line. So this is called, remember the slope of this line right here, because it goes through 2 points on a curve, is called a secant line. Okay. Any questions on that? So how do we find the slope of a secant line between this ordered pair and this one? Let's see, this ordered pair I think is something like 4, 17, it looks like. Well, we could just use the slope formula, y2 minus y1, right? So we would use 17. In fact, let's write it this way. 17 would have been f of 4. So f of 4 minus f of x all over 4 minus x. But that's the same thing as 17 minus f of x all over 4 minus x. Okay? Well, the slope of the green line certainly doesn't match the slope of the red line. Right? So what do we do to make it a better approximation? Yeah, we're going to take this point and bring it in closer. Okay? Specifically, rather than think of moving the point in, what I'm going to think about is moving the x value of the point inward. So if I take this x value and I start to approach 4, okay, my y values will be starting to approach some number, and we'll ask the question, how is this new expression behaving as I do so? Okay. Notice I can't plug in a 4 into the secant line. equation. If I did, I would have f of 4 minus f of 4 all over 4 minus 4. What type of expression is that? Indeterminate form, right? So we can't actually plug in 4 into our secant line formula, but we can take the limit as x approaches 4. And that's it. Okay? So the definition of a tangent line at a point, the definition of the slope of a tangent line at a point is equal to the limit as x approaches a of f of x minus f of a all over x minus a. So I'm going to bring the x value closer and closer to a. That'll bring my f of x value closer to f of a, but this indeterminate form will often evaluate to something. And that will be the slope. If it does, that will be the slope of the tangent line. And in fact, I have to add to this definition, because I've written a limit here. Do limits always exist? No. So I have to always add to this definition, provided the limit exists. Okay. From here on out, I'll just write PLE, provided the limit exists. Okay. So if you go back to your notes from section 2.1, you don't have to right now, sorry. But if you do, you will see that we tried to calculate the slope of the curve, the slope of the curve at this ordered pair right here. This is the ordered pair 1, 1. Okay? And we did so by several different secant line approximations. Now we're actually going to find the slope of the tangent line. Okay, so here it goes. Okay, so the slope of the tangent line, let me write that a little nicer. The slope of the tangent line at x equals 1 is equal to the limit as x approaches 1 of f of x minus f of 1 all over x minus 1, of course, provided this limit exists. Well, this is the limit as x approaches 1 of, what's our function here in this case?
Parabolic.
Yeah, this is the x squared function. Okay. Minus, what happens when I plug a 1 into the x squared function?
You get a 1.
I get a 1 all over x minus 1. Okay. So right away, I mean, if you go back to your limit notes, this was the very first limit that we did, or maybe the second one. Okay. This is one of the first limits we did. Okay. And you see why we've been doing limits like this. Because we wanted to find the slopes of tangent lines and look at this type of expression. I mean, this is an indeterminate form. Okay. So this gives us the limit as x approaches 1 of x plus 1 times x minus 1 all over x minus 1. And all of our tools from the previous chapter are still in play. We can now, after we've canceled out the thing that was making this an indeterminate form, evaluate this limit through direct substitution. Don't lose sight of the problem when we get into the middle of the work. What did we just find? We just found that the slope of this red line right here was 2. If you go back and look at your notes from 2.1 when we first did this, we were approximating, and we got, oh, the slope is 1.9 or 1.99 or 2.001, and we said, what do we guess the slope is? We guessed it was 2. Well, now we've proved it using this limit notation. Okay. All right. Is that all I asked you to do on this problem? No. What did I ask you to do on this problem? I asked you to find the equation of the tangent line. So we just found the slope of the tangent line. Okay. Well, remember, how do you usually find the slope of the equation of a line? Find the y-intercept of the slope. That works. Sometimes that's a little harder to do, so we just take any old point and we use the point-slope form. Okay? So as a reminder, the point-slope form, the way you first learned it, looked like this. Okay? That's good. It's true. Nothing wrong with that. But I want to start tailoring this to a specific function. So rather than writing the ordered pair x1 comma y1 like we did in Algebra 1, let's write it as x comma f of x, right? What's that? The big kid way. Yeah, let's take the training wheels off. Okay? So here we go. We can write that the slope of the tangent line at the ordered pair a comma f of a will be y minus f of a is equal to the slope of the tangent line times x minus a. So we had, for our particular point, we had the order pair 1 comma 1, right? So this was our a, this was our f of a. So this would be y minus 1 is equal to 2 times x minus 1. Okay? Folks, I am perfectly happy with point-slope formula line if I ask you to give me an equation to the tangent line. Okay? This is just as valid as slope-intercept form. I can work with it just as quickly. I know the slope of the line. I can identify the ordered pair that it passes through, 1 comma 1. That's fine. My math lab will ask you to put it often into slope-intercept form, so go ahead and do so. Okay? So just distribute some things out. You get 2x minus 2, and then we get y is equal to 2x plus, 2x minus 1. Okay? I'm perfectly happy with this answer too. I'll never dock you for doing one or the other. Okay? But my math lab will ask you to do this one. I find that sometimes the order pairs that your function passes through are fairly messy. It might go through the order pair e comma the square root of e minus 7. And so I would rather just leave it in this format rather than trying to manipulate the rest of that algebraically. Okay? All right. I need you to start keeping track of the various tasks for this unit. Okay? The first task that we've had in Chapter 3 now is to find the slope of a tangent line. The second task that we've had is to find an equation to the tangent line. Those two tasks are very similar, right? But just pay attention because they're not the exact same task. Okay? Please, please, please read the directions in my math lab. Okay? Sometimes it'll just want the slope, sometimes it'll want the entire equation of the tangent line. Okay? Folks, we're a little bit behind here, so I'll go ahead and just to give you these equations. Okay? I'll give them to you in point-slope form. So this was y minus 1 is equal to 2 times x minus 1. This was the one that we just found. The slope of the tangent line when x was 1. The equation of the tangent line when x was 1. This one would be the equation of the tangent line when x is 2. And this would be y minus 4 is equal to 4 times x minus 2. And this last one right here would be the equation line at x equals 3, the equation of the tangent line would be y minus 9 is equal to 6 times x minus 3. Okay? Folks, I just did this procedure. I found the equation of the tangent line at all these different x values. Okay? So this was, let me just reiterate, this was at x equals 1, this was at x equals 2, and this is for at x equals 3. Okay? I encourage you to, on your own, repeat this procedure and get these 3 answers. Okay? The work is identical to the work on the previous page. Okay? So repeat it, see if you can get those 3 answers. Something I'm kind of interested in is how the slopes of those tangent lines changed as I moved my x value around. Okay? It seems to me that we might be able to come up with a general formula for the slope of the tangent line at a given x value. what do we think the slope of the tangent line is at some x value?
I minus x squared equals 2x x minus whatever. I'm seeing a pattern pretty much.
I'm seeing a pattern too. When x was 1, what was the slope?
It's double.
And then when x was 2, what was the slope? Double it. And when x was 3, what was the slope? Double it. So I think it would just be 2x. Okay. Keep that in mind because right now we're finding slopes of tangent lines at individual points. That's a skill you got to learn. But later on we'd like to streamline this. Okay. All right. I think that was all on this page. So we'll turn to next page. I want to show you what we were doing here on the very first page, though. You don't have to flip back to it. I'll just show you what we were doing. Okay. What did I do? Well, I thought of moving my x value closer and closer to what? In this definition down here. In 4 in this case, or in general, we moved our x value closer and closer to a. That's how we found the slope of a tangent line, right? We took our slope formula and moved the x coordinate closer and closer to the fixed a value. There is an alternate way of thinking about this. Rather than saying x is getting close to a, let's think about the distance between this point and this point. What's the distance between these 2 points doing? The distance is going to 0. Right? The distance between the 2 points is approaching 0. Okay? So that's an alternate way of thinking about this. And because of that, we can give a different definition to the slope of the tangent line at a given point. Okay? Why do I give you 2 definitions? To confuse you? No. Sometimes one definition is easier to work with than the other. Okay? These problems involve a lot of algebra. Okay? And sometimes the algebra required to do one problem is easier than the algebra required to do it with the different definition. Okay? So anyway, here's the alternative definition. We're going to say that the slope of the tangent line at x equals a is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Provided the limit exists, right? Anytime I write a limit, I've got to assume it's going to exist. Okay. What's that? I heard it?
I said now we have the quotient formula.
No, not quite. But this was called the difference quotient, right?
Right.
So this piece inside of the limit was your difference quotient. Okay? It was your difference quotient from college algebra. What's different about this? We're taking the limit as the h is going to 0. Okay? Let me just show you kind of more in a more streamlined way where we got this definition from. Okay? So if here we had a curve, and we're talking about this ordered pair right here, a comma f of a, and we're trying to approximate the slope of the tangent line right there. Okay? So what we did was we took some other ordered pair right here. Rather than labeling this other ordered pair x comma f of x, I'm going to label this other ordered pair a plus h comma f of a plus h. Right? Because h stands for some small quantity usually. Okay? And then what does h do? H gets smaller and smaller. As h gets smaller and smaller, this ordered pair gets closer to a comma f of a. So it's the exact same idea, but given in a different formula. Okay? All right. So, number 9. Let's find an equation to the tangent line of the parabola y equals 3 over x at x equals 4. Okay, I do this because this is the way the author often gives functions. This is the way my math lab often gives functions. I would like to immediately give this function a better name. I think I'm better at naming it than our book. Let's label it f of x, or g of x, or h of x, but something other than y. Because eventually we're going to have an equation of a tangent line, and that's going to have a y in it. And I'd like to quickly be able to differentiate between the two. Okay? You don't have to relabel these like I just did, but I find it just helps you sort things a little better. Okay? So let's look at the graph of this hyperbola. The graph of this hyperbola looks something like this. It should pass through the order pairs 1, 3 and the order pair 3, 1/3. Okay. And what are we trying to do? Well, we're trying to find an equation for the tangent line right here at x equals 4. Everyone understand the question?
The second point, right? 3, 1/3.
No. No, it's not. Thank you, sir. This is the order pair what? 3, 1. Thank you. Coil, right? Thank you. 3, 1. Yeah, I don't know why I thought it was 1/3. Good catch. Any questions on the picture here? So we've got a hyperbola. I'm trying to find the slope, the equation of this tangent line right here. What should the slope of my tangent line be? What sign should it have?
Negative.
Negative, right? So immediately maybe start kind of guessing at what an answer should be. Okay. In fact, I think we could probably say it's going to be negative and it's going to be less than a slope of 45 degrees, right? I mean, my picture's not the best, but it's going to be less than a slope of 45 degrees, so I think it should be less than -1, right? Sorry, in the absolute value sense, a number smaller than -1. Okay? Regardless, let's get started here. Okay? If I want to build an equation to a line, what do I need? I need to use my point slope form of the line, so I need a point, check. Well, I guess we haven't actually found the point. What's this ordered pair right here? This one right here that 4 goes through. That'd be the ordered pair 4, 3/4. Okay, good. Check. I got a point. Now I need a slope. Okay? And the slope of the tangent line is the hard question. Everything else is just an algebra 1 question. Okay? So what's our formula for the slope of a tangent line? So let's take the alternate definition. We could have done, I could have had, so I heard maybe some people starting to say it. I could have had x approach 4, okay, but I'd rather do this one in this case. Okay. So this would be the limit as h approaches 4 of f of 4 plus h minus f of 4 all over h. Okay.
So h approaches 0 or h approaches 4?
Yeah, let's look at that. So when I use the alternate definition, the way I like to think about it is the distance between the 2 points is going to 0. If I were using the other definition, which I could certainly use, if I were using the other definition, I would be saying the slope of the tangent line at x equals 4 is the limit as x is approaching 4 of f of x minus f of 4 all over x minus 4. So here, my x coordinates going towards 4. In the definition that I'm currently using, which is the exact same idea, my distance between the 2 points is going to 0. My distance between the two x values is going to 0. All right, so let's look at the specifics of this function. We get the limit as h approaches 0 of 3 over 4 plus h minus 3 over 4 all over h. Folks, hopefully you see that we have an indeterminate form here. Can I just plug in a 0 for h? No. Some sort of algebra is going to be required. Okay? All right. Let me take just a minute to review something with fractions that many of you have forgotten. Okay? If I have the fraction 3/7 plus the, let's do minus just so it stays the same, minus 2/5 all over 8. Okay. I have two options for how to work with this problem. Okay. My first option is to get a common denominator for these two smaller denominators and combine them. Then I'll have a fraction divided by potentially another fraction, and I work with fractions. That's one way to tackle this. If you wish to do that, be my guest. Okay? I'm not going to show you that because I just don't want to show you two methods. Okay? I will be using this method for simplifying this. Okay? The method I'll use is I'm going to multiply by the least common denominator of all of the smaller fractions. Okay? So which of the, what do I mean by the smaller fractions? I mean this fraction right here, and I'm trying not to mess up my board, and this fraction right here. Okay? Those are the two smaller fractions. So what is that LCD across those two fractions? It would be what? 35. Okay? I would like to keep it as 7 times 5 because that fits better with my analogy, which is 35, right? Okay? So I'll show you this once. We're going to go through it slowly with numbers, but then the algebra gets messy quickly. Okay? So I'm going to multiply this by 7 times 5 over 7 times 5. Okay? In the denominator here, I just have 8 times 7 times 5, right? When I multiply fractions, I just multiply the denominators. Okay, everyone, once you get caught up, take a look up here, okay, because this part's very visual. Okay. I'm now going to distribute this 7 times 5 to both terms in the numerator. Okay. When I distribute 7 times 5 to 3 over 7, the two factors of 7 cancel. What am I left with? I'm left with 3 times 5. Okay. Then I distribute the 7 times 5 to the second fraction. What happens? The 5's cancel, and so I'm left with 2 times 7. Why did I choose to multiply by the LCD? The way I like to think about it is I'm clearing out the smaller fractions. If you do the LCD, you will perfectly clear them all out. Okay? And then you continue in simplifying the problem. But notice this has fractions within fractions. This is down to a single fraction. I like this better. Okay? All right. I say that because I'm going to do this same technique over and over again. And what you're not, I'm going to write this part and I'll write this part, but then I'm going to go from here to here, and I can't give a whole lot of explaining because there'll be x plus h plus 2 times x minus 5, and it's hard to talk about how those factors are canceling. Okay? So I want to see if there's any questions here. Okay. So do this problem a couple of times at the same time that you work this one. Okay? So what have I got? I've got fractions within fractions, right? So my trick, not my trick, I didn't come up with it, okay, is to take and multiply this by the LCD of all my smaller fractions. So what am I going to multiply it by? I'm going to multiply it by 4 times 4 plus h all over 4 times 4 plus h. Okay? If you get lost in this step, remind yourself why you're doing it. You're doing this step to clear out those smaller fractions. Okay? So let me do the denominator first. That's straightforward, I think. That gives me h times 4 plus h. Everyone okay with the denominator? In my numerator, Okay, so let me draw the little diagram that goes with it. I'm going to distribute here and distribute here. I multiply the LCD to the first fraction. The factors of 4 plus h cancel, and I'm just left with 3 times 4. Minus. Then I distribute the LCD to the second fraction, and the factors of 4 cancel, so I'm left with 3 times 4 plus h. Okay. Okay, let's keep working with that. So I'm left with the limit as h approaches 0 of 12 minus h, minus 3h, all over h times 4 plus h, which leaves me with the limit as h approaches 0 of minus 3h over h times 4 plus h. At long last, we can cancel out the factors that were preventing us from doing direct substitution. So I'm left with minus 3 over 4 times 4 plus h, and now I can actually do that direct substitution. So I get 4 times 4 plus 0, which gives me negative 3/16. Are there any questions on that? I'd really rather tackle the questions now rather than later, so now's a great time to ask them.
Are you just gonna, do you
Yeah.
prefer to, right before the final answer, leaving the 4 times the 4 plus h?
I mean, you could have distributed that as 16 plus 4h, that's fine.
Which is what I did. Doesn't matter what you say either way.
Nope, nope.
Because sometimes it's good to keep them unfactored, or keep factors out.
While I do this, I tend to keep things factored as long as I can, unless I need to expand them to cancel something. But that's just a general strategy. You can do it either way.
That makes sense.
Yep. If you do this procedure of taking limits and you arrive at minus 3/16, folks, you're good. Okay? Now, some of you have seen the rest of the story before. Some of you have been through calculus before, and maybe you can take derivatives a lot faster than I just did using the limit definition. You cannot do that. On your test, I will have questions where I say, using the limit definition, find the derivative. Okay? For other questions, you can use shortcut rules, but I need to know that you understand this procedure. Okay? All right. Are we finished with the problem? No. What have we found so far? The slope of the tangent line, which, let's go back to our picture. I'm sorry, folks. Yeah, I'm sorry. But you see that this line appears to have a slope of minus 3/16? Not a bad picture to go with it. Okay? Let's finish it out. Let's give the equation of the tangent line. Sounds like you're out of room. I'm sorry. All right. So we have y minus f of a is equal to the slope of the tangent line times x minus a. In this case, a is the number 4, so we get y minus f of 4 is equal to minus 3/16 times x minus 4, or y minus 3/4 is equal to minus 3/16 times x minus 4. And I would really, really like to park my answer right there and not worry about putting it into slope-intercept form. Okay? I would argue, though, if you're scared about putting that into slope-intercept form, then maybe you should practice. Because it's just adding fractions. But they're, you know. Okay. Any questions on that problem?
when you were determining the point for 4, comma 3/4.
Yes.
Where'd you get the 3/4?
Yeah, so this is the order pair A comma f of A. So how did I get the 3/4? So when x is equal to 4, I went ahead and plugged 4 into the function. Yeah. So that's why, I mean, but actually, that's precisely why I don't like to use this y equals 3 over x, just because that gets a little confusing. What did I just plug it into? I plugged it into the original function that we were given, y equals 3 over x. Great question. Others? Okay. All right. So I want to return to this idea. We're not going to spend nearly as much time on it as before. You're driving from here to Santa Fe. Suppose that's 400 miles. Okay. So where do we start off at? We start off at 0, 0. If this is time, and this is miles. We arrive at Santa Fe at the ordered pair. How long did it take us? 8 hours. So this is the order pair 8, comma 400. Okay. So what is the slope of this line? Well, the slope of this line is 50. How do you interpret that slope? It's 50 miles per hour. Okay. So as a reminder, to calculate average rate of change, you simply take the slope of these 2 points. 0, 0. At 0 hours, we've traveled 0 miles, and at 8 hours, we've traveled 400 miles. Compute the slope of that, and you've got your average rate of change, your average velocity. Okay? As a reminder, though, we're not interested in that answer. That was an Algebra 1 question. Okay? And the example I give is that when you pull out of the parking lot right there, okay, you're not going 50 miles per hour, hopefully. Okay? And when you go through the stoplight, when it's red, you're not going 50 miles per hour. Okay? So we're interested in finding your instantaneous rate of change, which the best example I have of that right now is what your speedometer says as you're driving. To be honest, though, the way the instantaneous rate of change is calculated by your car, it's actually just a very precise average rate of change. Okay? So even that's not perfect. What do we mean by instantaneous rate of change? Well, let's define it. Okay? The instantaneous rate of change, or the instantaneous velocity at a point at, let's say, t equals a, is simply the limit as h approaches 0 of f of a plus h minus f of a all over h. That's how we choose to define it, and that should look familiar because that's just the definition of our tangent line slopes. And remember, if you go back to your 2.1 notes, we said, hey, these are really the same 2 questions. Okay? The picture that goes with that is if I gave you some real position curve, okay, then finding the slope of the tangent line of a position curve is equivalent to finding the instantaneous rate of change, where this is time and this is distance. So I have no new ideas to present in this section beyond this. It's just kind of a, let's try it a different way. Let's look at it through a different lens. Okay? I think since we are a little bit behind, folks, I would like to go ahead and jump straight to number 14 now. Okay? If we get a chance, we'll come back and catch up a couple of those examples. But what we do going forward should help you get those earlier problems done. All right, here it is. Dear Diary Day. Dear Diary, today I learned the definition of the derivative. My life has changed forever. Okay. This is the first of the big calculus words after the limit. It's the word derivative. Okay. The derivative is just an idea that's encompassed by what we've already presented. Okay. The derivative of a function at x equals a. So let me just add fixed number. A is given by this definition here. It is the limit in fact, let's go ahead and denote it though. We write the derivative as f prime mark of a. F prime of a is equal to the limit as h approaches 0 of f of a plus h minus f of a all over h. You can fill in the blank, provided the limit exists. I'm emphasizing this fact that this is a fixed number, and this is especially important for today's lesson because you're going to get no time to regurgitate this before we jump into section 3.2. Regurgitate it, sorry, digest it. Digest this. Oh, that was a Freudian slip there. You're going to have no time to digest this before we jump into the next section. In this section, I'm defining what it means to be the derivative at a point. In the next section, we will define the derivative as its own function. And while I won't trip you up in certain instances, there are cases where you need to pay attention to the difference between those two ideas. So I'm emphasizing this right now. Okay? The alternative definition then is f prime of a is equal to the limit as x approaches a of f of x minus f of a all over x minus a. Oops, that's a lie. No, that's not. Okay. Of course, provided the limit exists. Okay? So, we've got a new notation, a new math notation here. Okay? This little prime mark signifies that we're talking about not f of a, but the derivative of f at a. So everybody together, this is the derivative of f at a. Let's try that again. This is the derivative of f at a. Okay? Please, don't even say f prime until you're exhausted saying the derivative of f at a. Okay? So practice saying these things in your head with the correct verbiage. Okay? Then you can get a little sloppy as you get really comfortable with it. Yeah?
So we're just saying the 14, 15 are the exact same derivative equation?
Yes.
So do you have a preference on which one?
No. No, I do not.
You personally?
Oh, do I have a preference? I tend to go towards this one first, and if I find the algebra is too messy, then I'll come back and I'll try this one.
But both of those theoretically should be able to work. Both at every equation.
There
You
is
could use
one
either
example
one, right?
where I don't think that I think that this one doesn't work well, and I've got a video of it already up for you.
Cool.
Great. Okay, so let's go ahead and find the derivative of f at x equals a for this parabola here. So, I'm asking you to find f prime of a. For 1 point, out of 5 or 6, for 1 point, show me that you've learned the definition. Okay, give either definition. This is equal to the limit as h approaches 0 of f of x, f of a plus h minus f of a all over h. You just got a point out of 6. Okay?
So
Yeah.
on 14,
Uh-huh.
is it the limit as x approaches 0? So up one more.
No, this is h approaches 0. So this one's 8. This is the distance between the two. And this is the x values approaching the fixed value. So let's look at it like this, right? So if I have some function here, and here's the order pair a comma f of a. Okay? I'm going to take some other point right here, x comma f of x. Okay? But I could also simultaneously talk about the distance between these 2 points. What's their distance? Their two x values are h apart from each other. So either x is approaching a, or h is approaching 0. Those two things are happening simultaneously. So they're the same idea. Yeah. Any questions on that? Okay. All right, so I'm using this definition of it. Okay. and this is usually my go-to definition, but either one will work in this case. Okay, and I encourage you to maybe try the alternate definition after this. Okay. But we have the limit as h approaches 0 of -7 times a plus h quantity squared minus 3 times a plus h plus 1 minus -7a squared minus 3a plus 1 all over h. Folks, if I lost you on that step, I don't mean to be mean, but you should have come see me last week. Okay? Because this is so important. Now, if I did lose you, it's not the end of the world, but then come by and see me tomorrow and we'll do what we can to catch you up. Okay? All right. I've got quite a mess here. We've got -7a squared minus 14ah minus 7h squared minus 3a minus 3h plus 1 plus 7a squared plus 3a minus 1 all over h. Folks, at this point, I think you should just be doing it on your own rather than copying me. Okay, copying's harder than doing it at this point. If you're lost, go ahead and copy it, but I mean, it's going to be easier for you to work through some of these than it is for you to copy my work on the board. Okay? Now, because this is a polynomial, now be careful, our hyperbola from before wasn't a polynomial. Okay? Because this is a polynomial, I know I'm on the right track if every term that doesn't have an h in it ends up canceling out. Okay? That's a nice little pat on the back. I know I'm on the right track. That gives us the limit as h approaches 0 of minus 14a h minus 7h squared minus 3h over h, which gives me the limit as h approaches 0 of minus 14a minus 7h minus 3, after I can't factor and cancel out the h's. Okay. Well, what was preventing me from doing direct substitution all along? That factor of h in the denominator. It's no longer there, so we've got a continuous function here, so we can go ahead and evaluate it through direct substitution. So this just gives me minus 14a minus 7 times 0 minus 3, which gives me minus 14a minus 3. That's the derivative of this function at x equals a. Okay. Okay. So I can give the tangent line one more way. Okay, so instead of saying y minus f of a is equal to m times x minus a, I can now go ahead and say f prime of a times x minus a. And this is probably from here on out the best way to give the equation of the tangent line. Okay, let me just write that the best way. Because it's using this f prime notation rather than that m subscript tan notation.
We would just plug in negative 14h. I mean,
Yeah, so if we were doing this for the same problem, then yes, you could do that, but it's nicer to actually have specified a number for what a is. So I'm not going to do it abstractly. Yes, but I think since for this I'm not necessarily continuing down to the same with the same information from 16. Okay.
So the derivative is in the slope of the tangent line? Or is
Very good. Yeah, go ahead and say that again.
the derivative is the slope of the tangent
The
line?
derivative
Or is
at a point is the slope of the tangent line at that point. Okay? That's exactly right. The derivative at a point is the slope of the tangent line at that point. Okay. So let's go ahead and find an equation to this tangent line. Okay. So we're going to use y minus f of negative 1 is equal to f prime of negative 1 times x minus 1. Oops, times x. Oh. Times x minus negative 1. Okay. Well, we said before that our f prime of a was, help me out, what was that? It was minus 14a minus 3. Okay? So for those of you who do already know differential calculus, you can check your answers to these problems. Okay? You check by taking the derivative of that. Yes, indeed, that's what you get. Okay? So anyway, what would be f prime of negative 1? It would be minus 14 times negative 1 minus 3, which is negative 11, I think.
That's 11.
Positive 11. Thank you. Okay. And what is f of negative 1? If we plug, so be careful here, folks. For those of you who haven't done this yet, I've got f primes and I've got f's. You cannot mix the two. Okay? Remember how I've been harping on labeling things this whole time? I need to know when you write something down whether you're talking about the function or the function's derivative. So you need to label things correctly each time. Okay? So don't just start writing chicken scratch. Always start off with the name of the thing you're working with. Okay? So what is f of negative 1? So folks are saying negative 3. Let's see, this is 3, 4. 4 minus 7 is negative 3. I agree. Okay? So this gives us that the equation of the tangent line would be y plus 3 is equal to 11 times x plus 1. And again, I'm perfectly happy with you parking your answer there, or you could put it into slope-intercept form. I don't think I want to say anything about 19. Let's go ahead and do 20 real quick. Here's a quick example of how we could, yes?
So you basically just found the point in the slope and put it into the formula.
Slope point slope formula. Exactly. Exactly. So the way this differs from an algebra 1 problem is finding the slope did not involve using the slope formula per se. It involved computing the derivative, which had a limit in it.
Right.
Yeah. Good. Good observation. Yeah, so basically up above here I say that finding the derivative and finding the instantaneous rate of change are the same procedure. Okay? So suppose you own land and you rent space out for a flea market. Okay? The number of booths, F, that you can rent is modeled as a function of X, your price. Does that make sense? Okay. If you lower the price, you should be able to rent more booths, right? Okay. If you raise the price, you would rent fewer booths. Okay. For this particular model, okay, if you gave it away for free, how many booths could you fit on your property? 200. Or there wouldn't, you couldn't find 200 people that would set up a flea market tent for free. 200 is the capacity in some way. Okay. So find the instantaneous rate of change when x is 25. So what am I asking you to do here? I'm asking you to find f prime of 25. Okay. Well, this is equal to the limit as let's go ahead and do x approaches 25. Just use the other definition just once more for practice. So this would be 200 minus, let's write up the definition. So this would be f of x minus f of 25 all over x minus 25. So this is the limit as x approaches 25 of 200 minus 4x minus parentheses If I plugged in 25 here, that would be 100 all over x minus 25, which equals the limit as x approaches 25 of 100 minus 4x over x minus 25, which gives us the limit as x approaches 25. Let's see here. I'll factor out a negative 4. When I do so, that gives me x minus 25 all over x minus 25, which gives us the limit as x approaches 25 of the number negative 4, but the limit of a constant is just the limit, or is just the constant. How do we do, folks? It's warm in here. So many brains thinking so hard, you guys are just warming it up in here. Okay. I want to interpret this. Okay? The units on this are booths per dollar. Okay? Because look at the way this was constructed. F measures the number of booths, X measures the number of dollars. Okay? So the interpretation of this is at x equals 25, we lose 4 booths for each additional dollar. That we charge. Okay. This was not a very complicated function, and in fact, no matter what x had been, we would have gotten minus 4. I know we're going a little long here, folks. I'm almost done with this. No, I better stop here. You guys aren't going to like this one. So let's stop here.